Hello, Mindsetters, and happy National Science Week. I hope you're up and ready to learn more with us and learn extra. This is your show, Learn Extra Live, with me, Abram, and I'm not alone. I'm with Tracy. How are you, Tracy?
I'm well, thanks, Abram. How are you?
I'm feeling so good. What are we up to today?
Today we're doing a massive concept. We're going to be discussing atomic mass and the mole, which is a new definition that we'll talk about. So very, very important, Mindsetters, to stay tuned today.
And I believe it's more theoretical.
It is a lot of theory, and there's lots of calculations. I mean, obviously, we can do this in practice, but we actually have to weigh out things. But this theory is going to stand you really in good stead throughout grade 10, grade 11, and grade 12. It's kind of the fundamentals of some of the chemistry that we're going to be looking at.
All right. Well, let me tell the Mindsetters that they can join us on 4 ways. One, you can join us on Facebook. Our Facebook link is facebook.com/LearnExtra. Like our page, join the 48,000 learners that we have that are talking almost every day with us. Secondly, follow us on Twitter @LearnExtra. And lastly, you can download the notes for today's show on learnextra.co.za/live. Now, a question that I'm going to pose to you as a viewer at home there. Let us know. It is National Science Week. What have you been up to as a scientist who's watching this show? Let us know on Facebook page, and we'll share and see what are the scientists up to. What have you been up to, Tracy, anyway?
Absolutely. Well, firstly, preparing for today and making sure that all the science teaching that I do is top-notch. And I know there's plenty of things happening at different schools. So get involved. There's ESCOM Science Expo coming up. We've got lots of things going on.
I like that. Let's get to today's session.
Thanks so much. So if you'd come across to the board with me, what we've got is we're going to be talking about atomic mass and the mole concept. We're going to be looking at, specifically in this lesson, introducing the concept of a mole, and that's huge. We're going to discuss Avogadro's number and the molar mass as well. Avogadro's number, big fancy name, named after the person. Then we're also going to consider what's happening in a balanced equation, and we'll look at those kind of balancing numbers, those stoichiometric ratios, and always we want to tackle problems. Problems in this chapter are incredibly important. There are a large number of questions that you could be asked, and so it's fundamental that you know how to work with equations and solve problems. Let's get straight into it. Key concepts. We're going to be speaking about atomic mass and the mole, and I said to you that we're going to start with the idea of a balanced equation. So in a balanced equation, you've got the idea of reactants and products. Reactants would be on the left-hand side usually, and products on the right-hand side of this equation. And not only does it tell us what the substances are, but it also speaks to us about the ratio in which they react. So if you've got maybe 2 sodiums reacting with 1 oxygen molecule to form or whatever the reaction is, it's going to show you the ratio in which they interact. But what about quantities? And that's what we're trying to get to in today's lesson. We want to be speaking significantly about quantities. Now, when I say quantities, I'm meaning amounts. Because if you think about it, in industry, and I've written the word the industry, how much must we put in, and then how much are we going to get out? So, for example, if I was running a big chemical industry and I wanted to know how much product I'm going to get out because I want to budget how much I'm going to be able to sell and what the pricing will be, I need to know what I will get out for the amount that I'm putting in. These chemical reactions and chemical calculations based on reactions are so valuable. Okay? It's going to help the chemical engineers to make sure that they're getting the quantities right and that they're not putting in stuff that's going to be wasted. So let's go and define what we speak about as we speak about a mole. This is a new word, and the mole, and we abbreviate it. It's not much of an abbreviation. We just kick off the E at the end. But a mole is an SI, the international system, the SI unit for the amount of substance. And we would speak about a mole as like any counting number. So you can speak about, if we were talking about time, we could speak about time in minutes or seconds. We could speak about it in days. We could speak about time in months or years, okay, or decades. It's simply a counting unit, right? But it's not just not counting time, it's actually counting amount of stuff, of substance, of whatever the stuff is. We want to speak about how much stuff there is so that we can work out quantities. So the definition of a mole, it is the SI unit for the amount of substance. And the mole is this massively long number of particles, or better yet, we could say that number 6,022 times 10 to the 23 particles. And we give that number a name. It's called Avogadro's number. Okay, there it is, Avogadro's number. It is the his thought was that the number of particles in a mole is equal to the 6,022 times 10 to the 23. Now, would you agree with me that that is a massively long number? Okay, 60220450000, and I'm not going to even continue. It would be ginormous, all right? We don't ever try and write that number out. We rather would use scientific notation with the times 10 to the 23, because when we're trying to handle very large numbers, or for that matter, very, very small numbers, we want to work accurately and not maybe leave off a zero, which would be very, would throw out our calculations completely. We would rather use scientific notation. So make sure you know how to work with scientific notation. It's incredibly helpful. So the number of particles in 1 mole is equal to 6,022 times 10 to the 23. And you could be asked to work out the number of particles, molecules, atoms. I could add to this list. I could ask you to work out the number of protons. I could ask you to work out the number of electrons in any substance. Because if you know how many moles you've got, you can multiply by Avogadro's number, and that will give you how many particles. And then from there, we could take it further and work out how many atoms within each particle, or better yet, we could work out number of protons. And if I was to ask you number of protons, you would say, well, each atom has its atomic number, which is telling me how many protons are in each atom. So do you recognize that this is going to be a lot of maths, but it's simply making sure that you've got the theory behind it, that you could then use your calculator and work out how many particles, how many atoms, how many molecules, or even protons or electrons. So let's simplify this into an equation. I've got the equation on the board for you here, and it's a very useful one to work with. We are saying there n is equal to the number of moles, all right? We've got n is equal to number of moles. Remember, that's just a counting unit, okay? This n at the top is the number of, I'm just going to take this bit off, the number of particles in the sample, okay? The idea that if I've got in my sample however many times 10 to the 23 particles, or times 10 to the whatever particles, that is the number of particles in my sample. Whereas this number at the bottom is Avogadro's number. Because I could say however many particles divide by Avogadro's number will give me the number of moles of that substance. So let's try one of these. Remember, this Avogadro's number will be on your data sheet. Go and use the one on your data sheet. Okay? The idea is that I've written the number here, 6,022. Sometimes it's rounded off to 6,002. Use what is given to you on your data sheet, and then you know you're going to get your calculations exact as to what your teacher's after, or examiner's after. Let's get into some questions. So question 1, how many atoms, and I'm going to circle some words here, how many atoms are there in 3,4 moles? Immediately I'm writing n equals 3.4 moles of helium. Now I want to just write here helium. What do I know about helium? Well, I can go check out my periodic table. There it is. Helium up here. Sorry, we just need helium's up there. Helium is one of the noble gases, and so I know when it's not going to bond with anything. Okay, so going back to my page here, I've got the helium. It's not going to bond. It's not diatomic or anything fancy. It's just simply the individual atom. So how many atoms are in 3,4 moles? Well, let's work our equation. Always start by writing your equation down. So N is equal to the number of moles in my sample divided by Avogadro's number. What I want to do is now rearrange it to solve for this one, because that is how many particles, and specifically I'm looking actually at atoms in my sample, because how many atoms are there in 3,4 moles? So immediately what I'm going to do is I'm going to rearrange this thing, and we're left with number there. Number of moles, when I take this Avogadro's number to the other side, I'm going to need to multiply. So times NA, and that's a little subscript A. Let's plug our values in. What have we got? Well, let's write N is equal to 3,4. That was the number of moles. Okay. Multiplied by Avogadro's number. So that's 6.022 times 10 to the power of 23. And you would need to work this in your calculator. So let's grab our calculator. It was 3.4 multiplied by 10 to the power of 23 equals, sorry, I need to clear that. I didn't put the 6,022. 3.4 multiplied by 6.022 times 10 to the power of 23 equals, and there I have it, 2.047. So let's round off to 2 decimal places. And so I'm going to write there 2.05 times 10 to the power of 24. Going across here, that was 2.05 times 10 to the power of 24. And I want to go back and just check that we've got it right. 2.05 times 10 to the power of 24. Perfect. And we've got here particles. Now let's just check it. It was helium, so therefore 2.05 times 10 to the 23 atoms, because that was what the question was asking me. Okay, final answer I'm happy with. Let's try another one. Question 2. How many particles are there in 0.5 moles of copper? So, very similar. Let's work through this again. Number of moles is equal to number of moles in my sample, N, capital N over NA. I'm solving for N, so it's small letter n multiplied by Avogadro's number, and it's going to be 0.5 times 6.022 times 10 to the power of 23. Let's go across to our calculator. Clear those. 0.5 multiplied by 6.022 times 10 to the power of 23 equals 3,011 times 10 to the power of 23. So going back here, let's write our answer. 3.011 times 10 to the power of 23, and that is atoms or particles, whichever it is. The idea behind Avogadro's number is that that is the number of atoms, or the number of particles, I should rather say more generally, the number of particles in 1 mole of substance. So what we're going to need to do is we could take any number of particles and work out how many moles we can get. There are lots of different questions based on this, and we'll try some more after a short break. Abram.
Thank you very much, Tracy. As we're about to take that ad break, I just want to say hello to all the mindsetters that are watching, especially Apua Morgan Makatini and Libya Lishono saying they are watching the show and enjoying the show. Highlight you and tell all the other mindsetters that you know the great times to tune in right now, because we're doing more stuff after the break. But as we're about to take that break, here's another a quote that I want to share with you, a science quote. It says, life is an experiment, but you can only know that experiment after you've tried it so many times. So keep on trying, because science, it is life. See you after the break. Welcome back, Mindsetters. I hope you're up and ready to even learn more. If you haven't downloaded the notes, go to learnextra.co.za/live and get your notes right now. As Mr. Albert Einstein has said, that education is not the learning of facts, but it is the training of the mind to think. We are trying to make you guys think at home. So think. If you have any questions, feel free to let us know via our Facebook page, which is facebook.com/learnextra. Over to you, Tracy.
Thanks so much. And Mindsetters, I really hope you are engaging your minds and thinking about these things. So let's tackle one more question on this topic. Question 3, how many moles are there? So now I've changed the question around significantly by asking you not for how many particles, but now I'm asking you number of moles. So immediately I've got my equation, number of moles over Avogadro's number. Are there in that number of molecules of carbon dioxide? Okay, so we have got this big number. This big number here is the number of particles in my sample, the number of molecules in my sample, which means I can come along and plug this in to my equation, and it was 2.45 times 10 to the power of 23 particles. In 1 mole, I know that there is Avogadro's number of particles, so 6,022 times 10 to the 23. Okay, so we've got how many in 1? Well, the total divided by how many particles there are in 1 mole. And so we can go along to our calculator and clear those. It was 2.45 times 10 to the 23 divided by 6.022 times 10 to the power of 23 equals, and I want it as a decimal, so 0.406, but I want this to 2 decimal places. That's usually how we work things. So 0.41, and immediately I can write here 0.41 moles, that is my unit, of CO2. Okay. Have I answered the question, how many moles? Yes, I have. That is my final answer. Right? Let's go to now a new equation that I'm going to talk to you about.
I have a question for you, Tracy,
Yes,
before you move
sure.
on. It's from Jablila Caroline. She says, am I going to be wrong if I always round off my numbers to 2 decimals? Because on the last question that you didn't round off.
I didn't round off. I was being lazy. I didn't round off. You're absolutely right. I probably could have. You know, this one was, I think here, 3.011. So times 10 to the 23 atoms, I think it was. Absolutely fine. 2 decimal places is usually what would be acceptable. Check with your teacher. I would be happy with 2 decimal places. Sometimes I'm just lazy though and don't round off. So sorry about that. Good question. Let's go on to talk about molar mass. All right. So now we've had the number of particles in 1 mole. What about the mass of something of 1 mole of that matter? And it's pretty straightforward. If we go along and measure the relative atomic mass of any element on the periodic table, we have 1 mole of that substance. So for example, I'm choosing 1 mole of magnesium. I've already agreed with you that 1 mole of magnesium will be 6,022 times 10 to the 23 atoms of magnesium, or particles of magnesium. But what about the mass? Well, coming across to the periodic table, I'm going to jump across. This number that we have at the bottom here, well, in this case, it's the bottom of my equation. that number there at the bottom of my periodic table, check your periodic table, that number is talking about copper's relative atomic mass. If I go find magnesium, here it's magnesium 24, all right? Your data sheet, this one only has two rounded off numbers. Go and check. We usually are wanting to work to 2 decimal places. Thank you for that question. So definitely make sure that you're working with the data sheet that you are given, all right? Because we want to try and be as accurate as possible. So this one is rounded off to 24. My notes, I think I've got rounded off to 1 decimal place. But notice here, you've got, that is this 1 mole is the same as the relative atomic mass in grams that we could measure out. So if I was to go to a very accurate scale and measure off 24.3 grams of magnesium, that little lump in front of me would be 1 mole of magnesium. Okay? If I was to measure off 12 grams of carbon, that would be 1 gram of carbon. If I was to measure off 32 grams of sulfur, that would be 1 mole of sulfur. Okay? The idea is that the relative atomic mass from the periodic table, if we were to measure it off, is this equivalent of 1 mole of that amount of matter. So, I now have a concept of the molar mass of something. The molar mass, and some textbooks use the capital M, small subscript m, which is what I've used here. Some just use capital M. Go and check what yours is focused on. Is the mass of 1 mole of a chemical substance. The unit would be measured in grams per mole. Because if you think about it, we're saying, okay, there are so many grams in every 1 mole, which is the same thing as saying grams multiplied by mole to the power of -1. Grams per mole. Okay? Now, we can use that molar mass significantly in an equation. And I've got this equation here. Let's actually write it out again because I want us to talk about it. Number of moles is equal to the mass of my sample divided by the molar mass. Okay? Now notice here, this I'm speaking about of the sample, and this one I'm speaking about the number of grams in 1 mole, the molar mass. Okay? That is in grams per mole, and this one is in grams, okay, because it's the mass of the sample divided by the molar mass. We can use this to huge effect, because what we can do with it is we can calculate how many grams there would be in 1 mole, and then I can work out how many moles there are in some unknown mass of sample that I've got. So let's go into some questions, and I'm starting you off by asking you to calculate the molar mass of a variety of different substances. Let's start with oxygen. Now, I recommend to you that if you're asked to work out the molar mass of oxygen, that you write in the molar mass of this thing in brackets, because it's going to firstly help you to go and make sure that you've got all the substances in the equation. Now, oxygen is pretty straightforward, but it's also going to make sure that you've got, say, the correct number of particles or number of atoms of each thing in the molecule. For example, oxygen is diatomic. Okay, so the molar mass of oxygen, we've got to go across to the periodic table, find it. There it is, oxygen 16. Remember, you are going to be asked to use your data sheet. Okay, this one is rounded off, but we've got 16. But hold on, it's got to be multiplied by 2. So I'm going to put the 2 in front there and say, why? Well, because every oxygen molecule is diatomic. It's got 2 atoms within the molecule. So I've got to multiply by 2, and that's going to be 32 grams in every mole. So grams per mole. What about potassium permanganate? And I've put this in because many of you are going to say, oh, I can't do that. That's going to be impossible. Look at how many different elements I've got. it's going to be crazy. Don't worry. What you're going to just do is go and find the relative atomic mass for every single substance, and that is one of the reasons why I suggest that you put it in brackets, okay? Because then you can check, I've got potassium, I've got manganese, I've got 4 oxygens. Are you following it? So let's go and find potassium. Potassium is over here, 39. Manganese is going to be 55. There it is. And we need oxygen again, and I've got oxygen there. So manganese was, potassium was 39. And I'm now adding it with the 55 of the manganese, and then I'm adding to it the 16 for oxygen. But, hold on a sec, the oxygen, there were 4 of them. So notice I'm multiplying by 4. Okay? Now, you might need to come do this in the calculator, so let's go across, clear those. I'm going to start with the multiplying. Okay? So 4 times 16 is equal to 64. But I want to add to that 55, and I want to add to that the 39. Okay? 158 is my answer. So we've got 158 grams in every mole. Last one, calcium hydroxide. Let's go to the periodic table. Calcium is 40. There it is. Oxygen I've got is 16. And hydrogen, mine is rounded off to 1. So let's go back here. We've got calcium was 40 plus. Now, hold on a moment. Do you notice that within the substance I've got a bracket here, and I've got the 2 on the outside? That 2 is telling me that I've got 2 hydroxide ions, which actually means that I've got 2 oxygens and 2 hydrogens. So I need to multiply by 2 of the whole thing, 16 plus the 1 for the hydrogen. Okay, let's work through this. Well, it would be, that's 2 times 17, which is going to be, we've got, where's our calculator? If you'd prefer, 16 plus 1 is equal to 17. I need to multiply the whole thing by 2, and I'm adding it to the 40 as well. So 74 grams per mole. Excellent. Let's take this one step further in terms of doing some calculations. In a balanced chemical equation, that's key, the number in the front, okay, that stoichiometric number, that balancing number of the chemical symbols describes the mole ratio. And this is key. Very important, NB, NB. The ratio of the reactants to the products. And so what we need to do is be able to take that into answering our questions. So let's look at the first one. I've got a number of questions here. We'll do question 5, and then we'll look at taking a break. I've got here a lead sinker. So lead, I'm thinking, PB, has a mass of 5 grams. That is my mass of my sample. Okay? Calculate the number of moles of lead in the sinker contains. So my first question is, find the number of moles. Well, that's pretty straightforward. I would need to go and then say, give ourselves some room here. Well, the number of moles is equal to the mass divided by the molar mass. Okay? And I have the mass as being 5 grams, but I want to divide that by the molar mass. Well, this is for lead, which is lead metal, which is on the periodic table, so let's go and find it. It would be down here, PB 207. There it is. Okay, so we go back and we can plug in the molar mass of 207 grams in every mole. Okay, so how many moles would that work out to? And let's work it on our calculator. It was 5 grams divided by 207 grams for every 1 mole is equal to, give it as a decimal, 0,024. So 0,02 moles of lead. Now you might ask me, why am I going to write out that whole thing about of lead? Well, it's because a little bit later we're going to come to whole equations where we could work out the moles of different substances. So I would recommend that you get into the habit of working out the number, of writing what you're working with in each case. The next part of this question, how many atoms, okay, are there in the sinker? Well, I now have the number of moles, so I'm going to take that and work out number of moles is equal to the sample divided by Avogadro's number, which I can then take and say, okay, but then the number on my sample must be equal to the number of moles multiplied by Avogadro's number, which was 0,02, check it, yes, multiplied by 6,022 times 10 to the power of 23. So going back to our calculator, 0,02 multiplied by 6.022 times 10 to the power of 23 equals 1,204. So 1,20 times 10 to the power of 22. We've got there 1,02. Was it 1,2? Just check it. 1,2. I made a mistake there. Let's just take that out. It was 1.20 times 10 to the power of, I think it was 22. Let's check our calculator. 1.20 times 10 to the power of 22, and it would be atoms of lead. And what you're working out here is very, very useful, because what you're working out is number of atoms, and that can be helpful in terms of calculations. So I think we need to take a short break for now, and we'll come back and tackle lots more questions. So mindset is keep those thinking caps on.
As we're about to take that break, here's an interesting fact that I have about moles. It says 1 liter bottle of water contains about 55.5 moles of water.
Interesting.
Very interesting.
I wonder how many water molecules that would be. You could go work that out in the break.
And let's see after the break. Mindsetters, keep it tuned. Welcome back, Mindsetters. Now, before the break, we asked you, well, I gave out a fact which says 1 liter bottle of water contains about 55.5 moles of water. And Tracy, you're going to prove that to us.
I am, but only at the end of the show, so you've got to keep watching. I hope you've worked it out, because you've totally got all the skills to be able to do that.
Nice one.
Excellent, thank you. So let's go through some more questions. We've got question 6 here. Calculate the mass. All right, so mass, I'm thinking, this is small letter m, and I'm going to find it in grams. That's my unit. Of 3 moles of ammonium hydroxide and 4,2 moles of calcium nitrate. Now, I've asked these slightly challenging questions. Let's start with A, and A was asking me 3 moles of ammonium hydroxide. So first, I'm going to work out the molar mass of ammonium, that's a 4, hydroxide, OH. Okay, so let's work this out. Well, nitrogen, hydrogen, oxygen, and hydrogen. So let's go and find them. We've got nitrogen, 14, oxygen, 16, hydrogen, 1. Is that everything? Let's go back, write them in. Nitrogen was 14. I then have 5 hydrogens. Do you recognize it's 4 and there's another 1? So 5 times 1 plus oxygen, which was 16. So working this through, it's going to be, well, I can see the 14 plus 16 is going to be 30. 5 times 1, it's going to be 35 grams per mole of NH4OH. Right. Now I want to say, okay, well then what would the mass be? So my number of moles is equal to mass divided by molar mass. Now, as I work this one out, I'm going to say, okay, well, the number of moles was 3. The molar mass was 35, and I'm solving for the mass. So mass is equal to number of moles multiplied by the molar mass. Because it was dividing on the right, when I take it across the equal sign, it's going to do the opposite operation, which means it's going to be multiplying. So we've got 35 multiplied by, oh sorry, should be 3 multiplied by the 35. Check it, it was 3 moles, yes. And plugging that into my calculator, 3 multiplied by 35, 105. And what will the unit be? It was 105. What would the unit be? Well, I'm working out mass, so it's grams of NH4OH. Next one, part B, 4.2 moles of calcium nitrate. Part B, this was, well, I had number of moles is 4.2 moles. My molar mass, I have to go and work out. That's not going to be given to me. And notice it was calcium nitrate. So, Ca, open brackets, NO3, close bracket, 2. Now, do you notice that I've got 2 nitrate, the polyatomic ion nitrate ions, and 1 calcium. So we've got quite a bit to work with here. Calcium. We used it earlier today. I can find it. Its calcium is 40. Nitrogen is 14. Oxygen is 16. I think that was all. So going across here, we've got, well, 40 for the calcium. Plus, now watch out, a big number 2, because notice this 2 at the bottom here applies to all of the everything inside that bracket. So it's applying to the nitrogen and to the oxygen. So it's going to mean that I've got 2 nitrogen and then in total 6 oxygen, because it's 3 times the 16. Now, I want to recommend that you work out what's inside the bracket first and then multiply by 2 and then go through it. Just check that you're including everything, because sometimes when you just plug things in your calculator, you miss out stuff. So watch out. Think this through logically. Well, we've got 3 times 16. And that's equal to 48. I'm adding to that, 3 times 16. I'm getting 48. I'm adding to that 14. And I know that then inside this bracket that I've got to multiply by 2, it should be 62. Are you following it? So check it again. So I can multiply that by 2, get my answer 148, and then and add the 40. I can then check that I've got, so it's now 164 grams in 1 mole. And I've included everything. Okay? Watch out, these polyatomic ions can be quite tricky. Notice you've got the calcium, you've got 2 of the nitrates, so it's 2 nitrogens and 3 oxygens multiplied by 2, which is 6. Check that we've got everything, absolutely fine. Now, I need to actually answer the question. So that was all just prep work before we can answer the question. So The number of moles is equal to mass divided by molar mass. I'm wanting to work out the mass, so I say number of moles multiplied by the molar mass, and that's equal to, well, it was 4.2 multiplied by 164 grams in 1 mole. So we've got our trusty calculator. 4.2 multiplied by 164 comes out to 688.8 grams. 688.8 grams of calcium nitrate. Okay. That one's now done. Let's try another question, because these can be challenging. How many atoms are there in 84 grams of nitrogen N2? Okay. Now, very interesting question. We start off by working out the molar mass of nitrogen. Sorry, N2. And that's going to be equal to, well, I know each one is 14, and I've got 2 of them. So 28 grams in 1 mole. Okay. The next step I need to do is work out, okay, if I've got 28 grams in 1 mole, how many moles have I got? So number of moles is equal to mass over molar mass. The question is, have I got the mass? Yes, I have. Looking across over here, I've got 84 grams of the stuff. So 84 grams divided by 28 grams. And we need to check we've got it. It's going to be 84 grams in my sample divided by 28 grams in every mole of that sample is equal to 3 moles. So I've got 3 moles of N2. Has that answered the question? No, it hasn't. Not yet. Because the question asked me how many atoms. So watch out. We haven't yet answered the question. We've got to now take this one step further, and using Avogadro's number, we're going to work out how many particles. Number of particles divided by Avogadro's number. And so I've got number of particles is equal to N multiplied by Na. So I have 3 moles multiplied by Avogadro's number, 6.022 times 10 to the power of 23. It's a big number. Calculator, 3 multiplied by 6.022 times 10 to the power of 23. 1.81. You see I'm rounding that off? It would be 1.806, so 1.81 times 10 to the power of 24. So let's go. We've got 1.81 times 10 to the power of 24 particles. Check it. That's great. Is it done? No, it's not. Do you see how this can be lots of calculations, which means lots of marks? So make sure you're getting these right. Were we asked to work out the number of particles? No, we weren't. Go back and check it. We were wanting to work out atoms. And notice that nitrogen is diatomic, which means, let's draw a little nitrogen, 2 nitrogens joining together, making up a particle. So notice, if that is 1 particle, in each particle there are 2 atoms. So what do I have to do to my final answer? Well, that was just the number of particles. Surely I'm going to have to say, therefore, nitrogen atoms would be equal to 1.81 times 10 to the power of 24 multiplied by 2 to get to my final answer in terms of the number of atoms that I've got. So going across once more, there's my answer. I'm going to just say multiply by 2 and I can get my final answer. Or better yet, 1.81 times 10 to the 24 multiplied by 2. And I get there 3.62 times 10 to the 24. So 3.62 times 10 to the 24 atoms of nitrogen. 3.62 times 10 to the 24. The focus here is that you need to read the question very carefully. The idea behind this is we're looking at atoms. We're not looking at particles. And each diatomic molecule, okay, or particle contains 2 atoms. So make sure that you then know which ones are the diatomic ones. Okay, these can be quite tricky. Question 8. 9.62 grams of sulfur reacts with an unknown quantity of zinc according to the following equation. Zinc plus sulfur forms zinc sulfide. What mass of zinc? Okay, now this is interesting. They're asking us what mass of zinc will you need for the reaction if all the sulfur is to be used up? So the focus here is that we've got the reaction. And I want you to notice that it's a 1:1 ratio. That number is not written there because it's understood. You don't write 1x, you can just write x. Okay? In maths, the same in science, when we have an understood one there. So what you have to look here at, and I'm going to write 2 columns. I'm going to have zinc, and on this side I'm going to have sulfur. The sulfur they gave us, so I've got their mass equal to 96.2 grams, and I can work out the molar mass. That's on the periodic table. I know it's 32 grams per mole. I'll show you quickly. There it is, 32 grams per mole. So coming across here, we first have to work out the number of moles of sulfur. Okay? And we would do that by saying, okay, N is equal to the 96.2 grams divided by the 32 grams per mole. And do you recognize that you're going to get a number of moles of sulfur, and I think it comes out to 2.99. So you can round off to, that would be 3 moles of sulfur. It continues that number, I know it does. The idea is that then we need to take this one step further and say, okay, if all of that got used up, then how much zinc must I have had? And because we're now working with a ratio, and if I go back to this balanced equation, you would see it's a 1:1 ratio. So I need to write that down. This is a 1:1 ratio. So if I have 3 moles of sulfur, it must have reacted with 3 moles of the zinc. And so you can take this, by comparing the number of moles, you can take this across to work out number of moles of zinc. And then you can do the same equation to calculate, okay, if we have zinc as being 3 moles, what, and the molar mass of zinc, which you could go and find from the periodic table, and I actually can read it off for you, it's 65.4 grams per mole. I can then work out the mass of zinc that I must have added into the system. Do you recognize how we're trying to solve these in terms of calculations in real life problems? And that's what we're going to do next week in more detail. So if you haven't quite got this mole ratio vibe, keep focused. Thanks, grade 10s. I hope this has really helped you.
Thank you so much, Tracy. And according to the fact that I've given, the mind sitters have answered on the page saying 1 liter is equal to 1,000 grams. And then you divide that by 18, which is the number of moles. And then it's 1,000 divided by 18. Then you get 55.5. So thank you very much, mind sitters, for watching. We'll see you on the other side. Peace.